Okay, so thanks everyone for coming to what will probably be the last STAC seminar for the year. So we're very happy to have Jiancang here from the ISM in Tokyo, and he's going to talk about estimation diagnostics and extensions of non-parametric box processes. Please take it away. Hopefully the camera will track you.
Okay, do you have the microphone?
No so problem. The microphone should be able to pick you up.
My name is Jiancang Zhuang from the Institute of Statistical Mathematics. It is a national research institute located in the west part of Tokyo. So my research interest mainly one is plan process, another one is statistical seismology, and the third one is Bayesian analysis. So today I'm going to see something related to one of my focusing research topic. It's called box process. So I'm here is by the invitation from Dr. Feng Chen, and we have shared the same interest on Hawkes process. So I thank Chen Feng very much for his invitation, and I have been staying happily for nearly 2 weeks. Okay, let me start. Okay. Okay, that's good. No problem. So let me start from the concept related to plan process. So a plan process is usually defined as a random counting method over the Euclidean space equipped with a Borel sigma algebra. It is required for any bounded set. As a probability, we have enough number of points inside. The counting method is finite. It's probability 1, so it's called bounded finiteness. And also, plan process is simple if there are no overlapping events occurring at the same location. And for the concept used in plan process, I think one of the most important topic is the conditional intensity. It is the expected number given in the unit time and space, given the history up to time t, but not included t here. Here I assume h, the history at time t is left continuous. So this is the definition of the history filter of the history. So this conditional intensity is natural for forecast because the non-zero probability can be easily calculated by assuming there is no events in the future interval multiplied by something like kind of the other component of the we usually call location. So here the lambda is also close related to the martingale property. So this theorem or this equality is frequently used in plan process. So that is when we are dealing with the conditional intensity. So this expected to hold because this part is a zero mean martingale. So with also the likelihood of the point process can be written in closed form if we know the conditional intensity. So this is a typical written typical form of this one. So it is almost the same as the intensity, the likelihood function for the Poisson process. But what's lying behind is quite completely different from the Poisson process. This is more general. So the Hawkes process was proposed by Hawkes in the 1970s. And so at that time, it's just a kind of temporal model, the temporal point process model. So the conditional intensity says this process have a immigrant process. We usually call it a background process. So it is a Poisson process with a constant rate mu here. And each time we have one event. This event will excite a new non-stationary Poisson process. So we use a function g as the conditional rate for the occurrence rate for the excited process. So it can also written in the form of measure, random measure form here. So the mean rate of this process, so if it is stationary, we can calculate simply by taking average over all of the possibility of the past. So it is, then we have this equation, it gives the mean in mu divided by the 1 over the integral this part. So this one, this to have a solution of positive solution of lambda bar here, we need to require this integral to be finite or and less than 1. So if this one is less than 1, then the process is stable and stationary. So this is some simple property of the Hawkes process. And nowadays in application, the Hawkes process has many forms. So this is a kind of spatial temporal form. And they have multivariate form. So we have assumed some discrete types for the events. So it's also called multi-type Hawkes process. And also we can call marked process, in which the mark could be continuous type. So among the space-time marked Hawkes process, the most famous one is the ETAS model. So it is used to model earthquake occurrence. So this part is the magnitude distribution for the earthquake. And this part is a background rate. It is constant in time, but not homogeneous in space. And also this is the trigonal term. This part is something like productivity of events with magnitude n. So it is a kind of positive exponential function. And this part is 2. It's one of the famous empirical formula in seismology called Omori-Woods formula. And this part is inverse power. So we another in crime data analysis, this one of the model used is break-in burglary data in Los Angeles. So this is by Moeller in 2011. This is the first article to use Hawkes process to model crime behavior. So this is a kind of separable space-time for the background and the trigonal part. So also we have Hawkes model for epidemic forecasting and for social network behavior modeling. So in those days, the Hawkes process is not a simple model trying to describe the kind of trigger mechanism between events. So it is always, it's not just used as a kind of diagnostic tools to detect and to forecast the short-term temporal cognitive correlation between the one process data. So, okay, let's come to the estimation problem of Hawkes process. So the likelihood for the Hawkes process was appeared in the form by Ozeki in 1979, and also the Rossben in 1996 to prove the asymptotic normality of the MLE for quantum process. And for Hawkes process, we have some special technique to work with it. So we call it stochastic cluster. So look at this conditional intensity. So we can make something like kind of have the conclusion. The probability event J is a background, is from the background. We just use mu divided by lambda with the value, with their values at the occurrence time and location of that event. So also we can also we can have the probability even J is triggered by I by the relative contribution from event I at the occurrence time and location of J. So we also, from this one, we also have this formula, which means each event is as a background or triggered by one of events in the past. So to prove it, it's quite easy to prove. We can just use this one to assume a kind of random field taking value 1 of 0 with the probability, this one. So X is not predictable, but this part is predictable. So we can make the conditioning with some conditioning. We can prove that this part here, taking value 1 or 0 after that one, that it has a kind of compensator with a kind of derivative density function with this mu here, so that means the process we realized is a partial process, because this mu here is a deterministic function inside the stochastic conditional density. So we have some other explanation to explain the probability. So if we look at this 5G here, we can say, okay, there are 5G background events are observed in this location. And also if we see rho ij here, we can say event I triggers this number of direct spiron direct spiron at this time and location here. So in this way, each event is sliced into background and spiron slice. So with this, this is the meaning of this, another meaning of this formula here. So with those probability, Wien and Schoenberg and other people have proposed the EM algorithm for the Hawkes process. It is regard this one as a complete value, and ij is, ij means 0, means it's from background. Ij equal I means even j from I, and this is and after that one, so it's this complete likelihood can be replaced by by the expected likelihood given the configuration, given the probability of the configuration. So this is the those rho and phi here is just the probability conditioning on the whole observation. So this is a hold for simple Hawkes process, but not hold for the renew Hawkes process. So how in our estimation, we have some property here. So this mu here is a function, is a kind of, we do not know the form, the mathematical form of this function. So we have to think about something, do something non-parametric to estimate it. And so this, how we can estimate that part. So one thing is, if we trying to estimate the, without time to get the mean rate, mean spatial rate, we can just forget about time and then use kernel span and those kind of all non-parametric method to estimate kind of the rate of events here. For the background events, okay, we use the same one as the total, but we can weight each event by this background probability. And then the other part could be using the MLE if this mu is given. So those part are parametric part. So this is, then we can design iterative algorithm. We use likelihood to design to ML to do MML to use to maximize the likelihood, and then to estimate those parameters in the parametric functions. And then we carry out stochastic clustering orbiting to orbit the background probabilities, and then using the background probability with some smooth, but the kernel estimates here is using the kernel smoothing here. And then after we have this background here, so we go back to this one and make such kind of iteration, make this carry out such iteration until we have the convergence of the results. So basically, so in this method, finally developed grows to completely non-parametric estimation algorithm. So it's this first appear by Massan and Lenny in 2008. So this is they replace this part to assume all of the functions have a non-parametric form and non-parametric use the weight of rho ij events j is triggered by I. The probability event j is triggered by I to estimate the those trigger cluster terms. So this is the algorithm result. They just assume some initial gates of formulation, the orbiting, so the probability for all of the pairs, and then they estimate the background on the determinant in the trigonal part by using some non-parametric method. I usually use kernel or histogram. I think those two using the histogram. And then we can update the background rate and the trigonal response function and back to the step. So this is the algorithm use. So it's converged well, but there is no one to make a kind of proof about whether the solution exists or how fast it converges and what's its asymptotics, not yet. And so we're now putting something in applications. Let's check the crime data analysis. So traditionally, the crime data analysis, they have some mode one hotspotting models. So it is just gives a map where crime more likely to happen. So those models from the statistical view more like some non-homogeneous but Poisson process, but with stationary non-homogeneous Poisson process here. And they have another one called linear repeat. So it is a model once we have some crime in one location, and it will more likely to happen another crime shortly nearby. So this is we call near repeat model, and they also some leading indicator regression one. So this is more like kind of regressive analysis to find the crime occurrence rate, and as a function of local of something like local variables, such as something like the population consistency, population structure, and economic situation, land value, those kind of things. And the number 4 the model is the kind of risk terrain model. So it is trying to identify the risk come from the feature of the landscape. So what kind of landscape more likely to have crimes? So those are those traditional. So the Hawks type 1 process model was introduced by Moreland in this year, and so after that, Moreland published a series of papers to use Hawks model to predict earthquake, predict crime behavior. So it need to was mentioning. So those models come from the UCLA Rick Schoenberg's research group. So basically, a lot of application of Hawks process are from that group, and this group used the Hawks process to study wildfire, and also the social network is a study also from this research group. So this Hawks model combines the near repeat and Hawks voting model together. And so here is the models. This paper here, that's a 2000, should be 2011, yeah, I made a mistake. And so they assume separate background here and with the trade room part. So they use the data from Los Angeles. It's more than 5,000 reported residential break-in burglary data. And in this area, San Fernando Valley, Los Angeles, during those 2 years. So here is the final estimate. You got the X coordinates, you got Y coordinates. They have those kind of, I think this is a spatial and parent distance. So they have this form like that. So this part, in fact, is the size of the blocks of each house. And this is the space-time marginal so this is more likely the X distance, more like the street, the same street, something like that. And so for the time marginal of the response function, they have some shapes here. So I'm afraid this is something like kind of weekly, periodicity comes in the estimate of T. So this marginal of T, I will dealing with those kind of periodicity in the crime data later. So what I study is the robbery related violence in custom spend. So this is the area of the custom city in Spain. And so I plot the space-time plot. This is time for 2 years. And this is north-south direction. And time in days. And in the west-east direction. And this is a cumulative number of events. So it looks not so clustered, but we will check it in our Hawkes model. So what kind of Hawkes model we should use this time? So what I do is I assume the background is mu of t is a trend of the crime behavior within the 2 years. And then mu d is a daily periodicity. And this is the weekly effect. And then the spatial part is separated from the temporal part. And this part is the trigonal part, where I assume the space and time are separable. So to estimate, I also assume some normalization with those kind of functions. I assume that those components in the background part have to have average 1, and G and F, they are 2 probability density functions. That means they integrate to 1. Oh, sorry. And I also assume there are those two constants. Those 2 constants that just trying to make those functions identifiable. So here I also name them as relaxation coefficients, which will help us in the calculation and to obtain stable and robust results. So A here is the critical parameter, also someone called it boundary ratio. So what's new in this model in problem? One is periodicity, another is the introduction of the relaxation parameters. So for G and F, so those estimate, histogram estimate. Those histogram estimate, it was already known in the Martian Lin-Yin's paper, and so Ij here is a probability, even J is true by I. So this already known, but what happens if we trying to estimate the theoretical part? Then we make use of this formula. So what we do is we need design this predictable function, which is called innovation process. So what we do is, okay, we first design this h of t here, and so it is in this function here, and then we calculate. We take a small interval of t here, around time t here, and then we make the integration of this one. So we calculate the integration with respect to the point process, and then it is equivalent to the integral, to the integral of the normal integral, arithmetic integral of those the multiplication of those two functions. Finally come in this way. So this part, because this is a small interval around time t, it can be approximated by this one. This part is just a constant. So in this way, we can estimate the shape of this trend function. So after we design different innovation functions for the daily periodicity, we can define this way. So, so this is the weight is defined, the function can be defined this way. And we can also define the one for weekly periodicity, and this is the kind of weight we estimate effect. And this is the background part. The background part is simple. We can just use the background probability, even J is a background image. So this part become other part, temporal part will be integrated to constant. So after we estimate all those functions, and then we can do some normalization to normalize this one have average 1, this one have average 1, and this one have average 1, and so all of those have average 1. And those two can be normalized as probability density functions. So we still have two parameters, mu0 and A in the model, not estimated there. So it's quite easy. We just carry out some MLE procedure and then can design the EM algorithm in something like iterative algorithm to the whole model. So we first set up initial values for all of the non-parametric model, non-parametric function, and the relaxation coefficients, and we calculate the weight for all of the possible I and also the rho ij for all the pairs, and then we reconstruct the functions of those two in those four in the background part, and those F1 in the trigonometric part, and then we estimate the relaxation parameters u0 and A by MLE, and we stop if the results converge. Otherwise, we go back to this step for the other one. Okay, and so this is the results for the model. So this is the model we propose. We're trying to use it have a kind of improvement comparing to the one with non-parametric background, okay, but plus trigonometric part, non-periodic background and plus trigonometric part, and then we have periodic Poisson model and we have non-periodic Poisson model. What we can see is the trigonometric part, the effect of the trigonometric part is just making improvement in the likelihood with 100, and the periodical effect makes a kind of improvement in the likelihood up to 300. So that means which means the periodicity is higher than the trigonometric part. So during the estimate, we use some kernel smooths with age correction in extraction. And so this is the results from the model. So this is the trend, 2 years, increasing quickly, and they may have some control, decreasing state. And then this is the weekly effect. So those kind of robbery, what happens during the 0 here in Sunday, during Sunday and Thursday, Friday, those have some during the weekends. This is the daily effect. The daily effect here is 0 it means midnight. So early morning is very quiet. So it's the peak, always happens. One is at 2 o'clock after lunch, and the second peak is, the highest peak here is after dinner. So more likely to happen in the evening. And this is the trigonometric part here, and this is the trigonometric in space. If we look at A here, 0.3, that means among 100 of the crime, those kind of robbery, only 3 of them are triggered. So it's quite weak. Okay, this is the kind of spatial distribution of the map for the crime, the background rate. And so we can, how can we can make some diagnostic of the model? So this is because those kind of nonparametric estimate comes automatically. We can with the tools to check the model correct or not. So what we do is we reconstruct the background for the first year and for the second year, and then make the canal to find the difference. And what we find the difference is quite weak. This means the separation, when we separate the spatial part and the temporal part in the background, is quite reasonable. And we also trying to calculate the daily effect for each year, different years. They are almost the same. For the different seasons, almost the same. But for different weekdays, they got a quite a big difference. Especially for Sunday, it looks quite flat, which still have the evening effect, but it is quite flat. And also for Saturday, this green line is also not so significant as other days. So this is the effect. And also the daily effect is slightly different from downtown and the suburban areas. So the downtown may have kind of early peak, another peak, maybe before lunch or something like that. And we also check the weekly effect. So the first year and second year almost no difference. And we check the city center and the suburban regions, and we found in the city center, the weekly effect is very significant. So it's based on Friday evening. So why Friday is high? This is because Friday is the payday for the wages in Castro. So people may just wonder, okay, because some wages will be paid in cash to avoid taxing problem. So people have the cash for robbery, and also people who cannot get enough paid. So they may think about to get some money from others. So this is Friday effect. And this is also the daily, I think the trend effect for different regions. For the suburbs in the west, east, south, and north, they're almost the same. But in downtown area, they are something like kind of one of the time in the end of the year, and some changes. I'm not sure whether this one, maybe some influence of the control of the police force. So this is the triggering temporal response for there are three curves, one for each year, but almost the same. And also for the spatial part, city center and the suburban area region, and the one, the difference is not so big. So we can see that for the reference, for the response part, triggering response part, the model is sufficient. And so later on, those kind of models, those kind of periodical Fox model have been applied to the traffic accident in the UK smart motorway, and they have something like the location. Those kind of two of the intersection have the effect of the big one, and they also found about 7% of the accidents are triggered. And this one is another one done by for the spoil over for the domestic abuse, the reporting for the police. And in this paper, the author Laura Wombell found this A equals 0. That means almost no trivial effect, but the periodic part is very clear. So, okay, let me come to the end. Makes a summary of my talk. So this is the Hawkes process, and basically the key point for the Hawkes process is the stochastic clustering part. We use those two probabilities to do our normal, to do our non-parametric estimate. And when the model getting complicated, we design those kind of general weight. And F is here with the designed predictable process, which is called innovation. And also we use the stochastic clustering part to use histogram estimate to estimate each component in the model. And finally, we use the ELM algorithm to estimate to do the iteration to get convergence between each component and the relaxation parameters. And so in conclusion, the Hawkes process can be used as a tool for investigating causal encouraging correlation among discrete events. So to do that, we have 3 steps to do that. One is to design the model, and we can design the model according to the features of the observation data, especially the particular mathematical form of the Hawkes model, and which depend a lot on available empirical knowledges. And we also need to design the estimate, and we can use MLE if we are trying to do parametric estimate, or EM algorithm also okay. And to non-parametric, we can use the reconstruction method. And we need to improve the non-parametric estimation using kernel, some of the Bayesian method, whatever. And the last step is to diagnosing the new model. The reconstruction method can be used naturally as a kind of such a tool to check whether the model is true or not, whether it can be improved or not. Okay, thank you.
Very much. Are there any questions for Jiancang?
Yep, I've got some questions.
Perfect. Fire ahead.
So you showed a comparison of different models based on likelihood, but it seems to me that you should be using some kind of adjustment for the number of parameters, because you've got these little deltas. You didn't discuss how they were chosen, that effectively they're generating an associated number of parameters. Yeah, I'm a bit concerned about that.
Yes, I completely agree with you. The only thing is, I don't know how to do this.
Okay, that's a fair admission.
Yes.
I think there's a couple of interesting things here. Firstly, BIC is normally set up to choose model orders. And again, I was a bit unsure, but it seems to me you could do some parameter counts in your so-called non-parametric part. So that may be one way to manage that.
The most reasonable one maybe is something like a cross-validation method. But the cross-validation method is we need to spend a lot of computation time to do that.
Yeah, the cross-validation is computational hell, basically. I mean, I still think a BIC could be put together. Another approach would be SURE, Stein's Unbiased Risk Estimator. I've written a stack of stuff about that, although it's all in the engineering literature. But that's another approach, although it's a bit more difficult to use with a point process model. Okay, so that's a question that needs more work on it. So I have another question. I didn't see any QQ plots, time rescaling diagnostics.
I did it with a kind of transform time one, which is trying to use the inter-event time distribution, and because after the transformation, every inter-event time becomes a kind of exponential distribution, and then if we put, exponential distribution with the same rate, and then we can plot such kind of cumulative number with the transformed one. So it is used a lot in point process, and I did it in the paper, but not sure it. But I didn't show it in this talk.
Okay, but you're saying it basically looks pretty good.
Yeah. It looks pretty good. Yes.
Okay, all right, that's interesting. Now the other thing is I missed the G function. I wasn't completely clear how you were modeling that.
You mean this one, this G function here?
Yeah, exactly. Yep.
It is a kind of nonparametric estimate. It is estimated in this way.
I see. Okay, so yeah, all right. I think there's other approaches. So I've done a lot of work using Laguerre polynomials.
Yes.
That gives you a parameterization with a handful of parameters. That's our experience, but it also gives you the enormous flexibility that you can get with a basis expansion. So that might be worth looking at. Again, using step functions is going to, introduce edge effects and all that kind of thing. But that you did indicate in the last slide that, you're going to look further into that.
So using the Laguerre polynomial is one of the, in early time of the Hobbes process. This is Hobbes in Hobbes model. But for real numeric calculation, when we estimate the parameters, the Laguerre polynomial may have some negative values. So this is, if this happens in the point process estimation, it always crashes the optimizer.
Yes, okay. I understand what you're saying. I guess the way that we do it is we're basically always using multiplicative style EM algorithm. So
okay.
we don't have that problem.
We put exponential, exponential function of the Laguerre polynomial.
Oh, I see. Well, yeah, you could do that. You can go nonlinear, but what I'm saying is with the regular Laguerre, if you update the parameters with a multiplicative EM, then you guarantee the positivity, you don't have any problem.
Yes.
Okay, yeah, that's all my questions. Anyway, very interesting stuff, very interesting looking data sets, and obviously challenging computational effort to, get everything to work. So be interesting to see further development.
Okay, are there any other questions?
Yeah, so for the Spain prime example, the branching ratio was 0.03. And I guess we have a really flexible background rate. And if you included another function in that background rate, I guess the branching ratio could go to 0. I guess how do you sort of decide to choose that background rate?
No, this is because when we're looking those kind of iterative things, so the background part always trying to to give something like kind of quite smooth in background in time. But this triggering part just trying to get the correlation pairs, very short time, short distance. And so this is the trying to catch different part during the estimation procedure. Also, when I'm doing the background part, the kernels, when we're using the kernel smoothing, the kernel is much larger. The bandwidth is much larger than this part when we estimate for the trickle part. So as one of the questions for the model comparison, another parameter when we're using kernel, the bandwidth is one of what kind of bandwidth is the best one to choose. So in this one, what we choose is okay. We just do it according to the resolution of the data. For example, if for daily effect, so we need those kind of to be smooth up to 10 minutes to half an hour. So this is the bandwidth for the daily. For the weekly, maybe we need several hours, 5, 10 to 10 hours as bandwidth for the weekly effect. But for those trend, we use something like 2 days to 5 days as bandwidth to estimate the trend. So this is the rule we will be using. But for the triggering part, the one we use is very much shorter than the daily.
Any other questions?
Look, I've got another one. So you've got a spatiotemporal data set. Do you get a situation where you're having robbery at the same time, but in different places?
If we have that one, basically, we just make, slightly change the time, make a kind of short time delay and lag between those two events, trying to avoid something like kind of mistake in the likelihood computation.
Yes, because of course the underlying assumption is that you cannot have two events in a tiny time interval. And I think actually this is a major problem with current point process models. I've done some work looking at coincidences because I think these coincidences actually occur a lot in real data. And because we're increasingly getting these larger data sets, I think they're going to be even more common. And I think the point process community should be putting some energy into that.
Precision, data record precision. Once if we have this one, we can, if for example, if the record is just in minutes, so we can bring back something like a half minute, negative half minute, positive half minutes, kind of randomly, uniformly distributed random variable as a rounding error back to the data. So this is what I always do. Especially it happens a lot with earthquake data. Earthquake data are always located for it's the precision of a percent of degree. So if such thing happen, I usually bring the rounding error back to the data and add the rounding error to the data. So this is one to avoid the trouble we estimate the likelihood.
Yeah, I think it depends on the kind of data. So I have worked with brain data, neural coding, spike trains, voltage spike trains. You are going to get a lot of coincidences in different parts of the brain, and you're not going to solve the problem by randomly perturbing those times, because you're then going to miss phenomena like synchronicity and things like this.
That's true.
So I think there's a lot of interesting problems there that need to be pursued.
So maybe we cannot do only just one copy of the random dispersion and generate many copies and evaluate the parameters to get a kind of overall estimate after we study all those random copies.
Right.
Yeah, so I think my question is related to Tom's question as well. With the estimated branching ratio to be quite small,
Yes.
the improvement in the log likelihood is, like 130. How many parameters do you have? I guess like how important it is to have that triggering effect. Like how many parameters do you have for the excitation component? Because otherwise you just use a homogeneous Poisson process.
So you mean parameters is because we have non-parametric estimate in the model. So we cannot say how many parameters here, but we just have those two, one for background, one for the triggering part.
Well, I meant like, can you just remove the triggering component because A is quite small?
It's no. If we remove the triggering part, likely to change the amount. So it is this thing, all those kind of triggering part always exist, no matter how I change the estimate from the background part. No matter how, if we just use the same set of kernel configuration to fit these models, and then those four models, so this we always use the triggering part to showing that, and almost the value is also very quite stable, around 3%. So this is I'm not sure the value I have is that one, but it shouldn't be too far away from those values. So
Just out of curiosity, how many, like the number of clients, like per day do you get?
So I have something like more than 5,000. So it's in 2 years. So that means 7 or 10 to 10 per day in average. So this which is quite big number, because Castron is one of the worst cities in Spain.
And I guess the branching ratio being quite small, so
It's quite small.
just do one hit.
Yeah, we can see also from here that those kind of jumps are quite small.
Okay, and there's a question from Fang.
You muted you are.
It's not
No,
muted.
I
it's
think
just
the audio is not working.
Audio here is not working.
It must be his side because we heard Victor. Yeah.
Okay. I think it's from your end, Fang.
I think
You should have come to campus, Fang.
Maybe we can defer the question, Fang, until another time when you're on campus.
Talking in the chat.
microphone seems to be okay.
No.
Or Fang, you could put the question in the chat if you like.
In chat box, please.
Is he closed yet?
Okay, we need to do this one.
No, it's fine. It will appear.
It's not.
Yeah. Fireplaces and stuff. Yeah, it's heritage, right? That's it.
something.
Elevated at least.
I can hear them.
So he asks for standard error for branching ratio.
She does not able to branch ratio. Oh man, this question. I don't know. Very good question. How we can estimate that? So in another way, when I was doing with the earthquakes, what I do is I just take the short-term jumps together and then to see the total length of the short-term jumps and then put up and then compare to the related and then compare to the number of the total number, cumulative numbers. And that's the branch ratio. I'm doing a kind of rough estimate from the graphics. So this one looks here, it's very hard to get to find the short-term jumps. So I'm really not sure how to estimate the error of this part. Both strip as last, that could be a good idea, last resort.
Okay, so I think there are no more questions. So please join me in thanking Jiancang.
Okay.
And yeah, have a good weekend, everybody.
Thanks.